Okay, so most of you are here. Yeah. Think some are back there. No. Yeah. Okay. So I think we can go on. Is it not too many? Some people are still missing, but
we are majority.
Majority is here. Okay. So we can go on. This section is entitled interaction modeling, and this is the only section I'm going to do today. And after that, you will have some time, at least 1 hour, maybe even more, for individual work, which is, I would say, the most important part of the course is individual work. And then after that, as usual, you will have half an hour for your own presentations, which is the second most important part of the course. So let's go to interaction modeling. So interactions play an enormously important role in any kind of system. So in any kind of system, we have interactions between different components of the system, as well as interactions between the components of the system on one hand and humans on the other hand. And of course, the second group of interactions occurs through a user interface. So here I'm going to talk about interactions in general, about interactions in a conceptual sense. So again, the viewpoint framework, I think it's good to remind now and then where we are, because the viewpoint framework is in my area, in my course, is as important as a business model canvas in some other courses that you had before my course. So we are now doing design. So we did analysis on Monday and Tuesday, and today we started with design, which means that we have become more technical now. And we are also now talking about software components or software agents, which is our umbrella term for software components. And as you remember, the viewpoint framework consists of 3 layers and 3 columns. The layers stand for the stages of analysis, problem domain analysis, design of socio-technical system, and finally prototyping of the system. And we covered on Monday and Tuesday goal models, role models, organization model, and domain model, which all belong to the stage of analysis. And today we move to the stage of design. And in the morning we covered agent models, which maps roles to agent types, acquaintance model, which models interaction pathways between agents of different types. And now we are going to talk about interaction models. So while acquaintance model captures interaction pathways between agents, then interaction models model the actual interactions between agents. But one precedes the other. So first we create acquaintance models to understand who goes with whom. So who interacts with whom, to get an overall picture that in our system these and these components interact with each other, and those components interact with humans. Now we model the actual interactions, but it is based on agent acquaintance model that shows the interaction pathways. And now we sort of elaborate these interaction pathways in terms of messages exchanged between agents. So as I said, interaction model represents messages exchanged between agents, And these messages can be viewed as interaction patterns between agents, because it is not just about messages, but it is about sending something and receiving something in reply, or about, for example, sending a request for quotes in business-to-business electronic commerce, receiving quotes, and then sending order after deciding which quote to accept. So it is about interaction patterns rather than just individual messages exchanged between agents. And interactions are based, as I said, on one hand on acquaintance models, because an acquaintance model defines interaction pathways, who interacts with whom. But on the other hand, interactions are based on responsibilities, because responsibilities defined for roles, they describe what an agent playing the role should do. And some of, actually quite a few of these responsibilities, they are related to interactions. So they describe indirectly what an agent should do in relation to other agents. So this is why I'm saying that interaction models are based on responsibilities defined for the corresponding roles, because some responsibilities they describe how an agent should relate to other agents. And there are two kinds of interaction models. First of all, there are pure interaction models. And secondly, there are protocol models. So what is the difference? Pure interaction models, they concentrate on just modeling what is going on between agents. So if we take two agents, two software entities that interact with each other, then pure interaction models concentrate just on the interactions that are going on between these agents. Or in other words, pure interaction models just concentrate on messages exchanged between these agents. Protocol models are different, because protocol models, they also represent interactions between agents. So they also represent messages exchanged between agents. But in addition to representing interactions, they also represent some elements of agent behaviors. So they are not behavior models. So we are coming to behavior models on Friday. But they just represent some elements of agent behaviors that are necessary for understanding better interactions between agents. And I will provide examples a bit later on. Okay, let's go to pure interaction models. And let's stick to our examples of Tamagotchis and social grocery shopping. Here is an example from the case study of Tamagotchis. There are three agents, three agent types: person, Tamagotchi. These lines here mean that we're talking about this example is about instances rather than agent types. I know from those of you with business background it may be a bit confusing, but actually the difference is very simple. For example, I am here an instance of agent type human. And all of you actually instances of agent type human, or for example that curtain there is an instance of agent type curtain. I mean this TV is an instance of the respective agent, not agent type. I am an instance of agent type human. The curtain is an instance of object type curtain. It is not an agent. It's not an agent yet, at least. And that thing here is also can be viewed as an object, I think. So it is an instance of the this object type smart whiteboard or something like this, even though no one has used it as whiteboard so far. But as I've heard, in principle, it can be used as a whiteboard. in addition to just showing some nice pictures. So this is the difference between instances and types. Or like this stand here is an instance of the stand type, because there are many stands of this kind around. Many of those have been produced, and this is just one instance. So, and here the same thing, that this model is about interactions between three instances. But it's not so important for your models. So when you come to modeling later on today and also tomorrow, then it's not so important. I do not actually require you to represent those underlines or to underline these names of agent types here. So what is going on here? So we have modeled interactions here. So first of all, there are interactions between a human agent and a software agent. And this interaction starts with a message by the Tamagotchi to the human saying that I am not happy. What is this? Well, this is a proactive behavior, an example of proactive behavior. Tamagotchi all of a sudden tells its owner that I am not happy, please do something about it. So this is an example of proactive behavior, because I mean it happens all of a sudden. I mean there is no immediate external event causing it. I mean it just happens. Okay, my Tamagotchi makes beep, and then the child has a look. I mean, what is going on? Oh, I mean my digital pet is not happy, so please do something about it. And now, in this case, the person has decided to ask her digital pet to visit its friend. So this is the way how that owner, how that person playing the role of owner has decided to act. How and why that a person has decided to act this way, I mean, this is not captured by this model. This is actually a task of behavior models to capture these kinds of behaviors. But I don't think it's even relevant here, because here we are talking about a human agent. So it's a decision making by a human agent that is usually not captured by models, even though in some systems it may be necessary to also model behaviors and decision making by human agents. So this person playing the role of owner asks his Tamagotchi to visit its friend. And now here are interactions between two software agents, between two Tamagotchis. So the first asks the second one, could I come to your place? So the answer is please come. Then they exchange greetings. Then the second, the first one gives a present to the second one, following the social policy that only the initiator of the visit can give a present. Remember, I actually mentioned this kind of social policy that for Tamagotchis, that only initiator can give a present. And it is similar, not similar, but it is belongs to the same category of social policies like the one of always taking flowers to weddings in Estonia. So the initiator gives a present, the host thanks for the present, then the initiator asks, may I play with you? The host says it's okay, and then this playing is captured with one interaction. Of course, actually it is a bunch of interactions, but here it is for simplicity, it is just captured by this one interaction. So this is a simple interaction model that captures interactions between three agents, one of them being a human agent and two of them being software agents. So very simple. This one looks a bit more complicated, but actually it is not much more complicated. So it is the same kind of diagram that represents interactions between three agent instances. And they are actually the same agents. The human agent playing the role of owner and two Tamagotchis playing the roles of my Tamagotchi and friend Tamagotchi respectively. And the difference that you can see here is, you see there are like two kinds of messages, like with this dotted arrow and with this solid arrow. And the message with a solid arrow represent physical interactions that occur through a user interface. So this is the difference. But the messages represented with the dotted arrows, they represent messages. So if my Tamagotchi informs the owner that I am not happy, then this is a message that it passes to its owner through its screen. I mean, of course, user interface screen is used for that, but it is still a message. It is still information that the owner gets from the screen. So that's why it should be modeled as a message passing, because it doesn't require any physical interaction. It is just seen, just hearing the Tamagotchi making a noise, the beep, and then seeing the message on the screen. But asking your digital pet to visit its friend, so this requires a physical interaction. So I need to operate on my Tamagotchi in order to do it. There are 3 knobs. I need to operate by using them in order to ask my Tamagotchi to visit its friend. And actually I need to do more. I need to connect these 2 Tamagotchis through infrared connection. This is also a part of the thing, but we do not capture it here. We capture just this physical operation of requesting my digital pet to visit another digital pet. And another difference you see here are those numbers. And they are just the numbers of messages exchanged between agents. It all starts with this message that represents a proactive behavior by Tamagotchi, with which the Tamagotchi informs its owner that it is not happy, and then it continues with a request by the owner to the Tamagotchi to visit its friend, and then the actual visit is represented through messages 3 to 11 here. So why do we need numbers? We need them in some situations because it is not always possible to represent a sequence of messages exchanged by just relying on how they are represented graphically. I mean, there can be situations where this kind of representation doesn't work because we cannot necessarily, always represent this sequence in just a graphical fashion. So, and that's why it is in some cases it is useful to have numbers attached to interactions between agents. But basically it is the same kind of model. So there is no fundamental difference between this model, UML style interaction diagram, and that model which is called interaction sequence diagram. So the only differences, actually the only 2 differences are that here we distinguish between messages exchanged and physical interactions, and here we have numbered interactions between agents. So are there any questions about these diagrams? Okay, so now let's go to a bit more complicated case, which is called interaction frame diagram. So the difference between the interaction sequence diagram you saw on the previous slide and interaction frame diagram you see here is that here we are not interested in actual messages exchanged or actual interactions between agent instances, but we rather represent the types of interactions between agent types, which means that here these boxes you see here, they are types rather than instances. What does it mean? Well, it means that here in this case that an agent of type Tamagotchi can send to another agent of type Tamagotchi a message of this type, could I come to your place? So this is the meaning. So now we are at the type level rather than instance level. So again, I'm not going to ask you to create models of this kind, but I'm just trying to give you an overview what kinds of interaction models are there. So this is why I'm talking about it, just to be complete about interaction models. So these are all the different types of messages, and they are not necessarily represented in the order of exchanging their instances, but usually, I mean, usually at least there is an attempt to represent them in the actual order of how this or in which these messages are exchanged, like you see here. And the reason why it is not always the case is that it's not always even possible to represent the actual order of messages in those kinds of interaction frame diagrams. For example, here you see one agent, the one Tamagotchi asks the other one, may I play with you? And then there are two answers here, okay, but the next one is, sorry, I'm not in the mood for playing right now. And this kind of situation can occur. And I mean, not both of them occur at the same time, so it's not possible, but just one of them is sent. So either the other Tamagotchi replies with okay, let's play together, or the other Tamagotchi replies with apology, sorry, I'm not in the mood for playing right now. But we still represent them in this diagram because they are both legitimate types of messages to be exchanged between two Tamagotchis. So this is the rationale for interaction frame diagrams, because in some because we need to represent possible messages exchanged between agents rather than actual messages that are exchanged between agents. So was this understandable, that we also need these kinds of diagrams to represent all kinds of or messages of all possible types to be exchanged between agents? Otherwise, in other respects, this diagram is quite similar to the previous one. So there is not much difference. You know, the notation for representing physical interactions and messages is the same, but there is no numbering here, and the names of agent types, they have not been underlined here. And these messages here, they do not necessarily represent a sequence of messages exchanged, but they represent just the types of messages exchanged, referring to possible interactions between agents rather than actual interactions between agents. And now the most complicated case is a protocol model that I mentioned in the beginning, and an example is shown here. So now this looks really technical and complicated to some of you at least, but it has clear principles that can be used for explaining this, or that it is based on. So here we have three agent types: person, Tamagotchi, and Tamagotchi. Just two types represented here, but I mean Tamagotchi and person. But this Tamagotchi, as we're talking about the Tamagotchi interacting with its friend, then I mean there are this Tamagotchi is represented twice. And here these interactions start in the way they did in the very first the UML style interaction diagram. So Tamagotchi informs its owner that I'm not happy, and in reaction to that, the owner asks his digital pet to play with its friend. And now there is a box option here. So what could it stand for? Option.
Can happen or cannot.
Yes, exactly. So this all the stuff inside this box can happen or not, and it happens when there is a connection between these two Tamagotchis. And now here again we are referring to a technology here. So there has to be a connection established by means of technology. I mean by means of infrared connection between those two agents. So that's why there is here is a condition connection operational. So if this condition is true, then all these interactions within the box occur. All the stuff within the box takes place only if this condition is true. In the given case, only if the connection between the two Tamagotchis is operational. Okay, let us assume that the connection is operational. Then the first Tamagotchi sends a message to the second one, could I come to your place? Now we come to another box, and that is alternative. So, and alternative, so what does it mean? It means that one of two things can happen now. So one thing is that the second Tamagotchi refuses the request for a visit by replying with a message, I am sorry, you are too young to visit me. And this is an example of following a social policy according to which only older Tamagotchi can initiate a visit. And if a Tamagotchi younger than the host initiates a visit, the visit is refused. So it's another example of a social policy. So, and these alternatives are marked here with the help of this dotted arrow here. So one alternative is when the visit is refused. So the second Tamagotchi sends the message, I'm sorry, you are too young, to the first one. And the second alternative is when the visit takes place. So in that case, the second Tamagotchi asks the first one to come, please come in, and then they exchange greetings. Now we come to the third box, and the third box is entitled loop. So as you can guess, this means that some interactions, they are repeated in a loop. And you can see there are two symbols here, number 1 and asterisk, and they mean that the loop is repeated from 1 to several times, meaning that it's not, at this point, it is not defined how many times the interactions within the loop are repeated. After this, or inside this loop box, there are two more boxes, and they are entitled, the first one is entitled option critical region. So option, well, as we already discussed, means that these interactions within the option box, they can take place or they cannot take place. The critical region means that there are two options. Either all of the interactions within the critical region box are executed, or none of the interactions within the critical region box is executed. So it means that either all of it is done or it is not done at all. And now the option option also comes with a condition. And the condition for option here is enough presence, meaning that the first Tamagotchi can give a present to the second one only if there are enough presents to give away. If there are no presents, then this will not happen. And this means that if there are no presents, the critical region here means that then none of those interactions within the box will take place. But if there are enough presents, then all of these interactions will take place. And when we go deeper, then here is another box, alternative. Alternative, you see, there are two options for reply. The second Tamagotchi can reply to the first one, I mean, after receiving a present. You see, the first thing is that the first gives a present to the second one, and now there are two options for reply. The first option is a very polite one. Thank you for the present. The second one, behave yourself. So why this kind of alternative? Do you remember that? I mean, I mentioned something about disciplining Tamagotchi on the very first day. Well, it is because undisciplined Tamagotchi can present another Tamagotchi with something like a snake, which is considered very impolite, very unappropriate present to give to someone else. And this is why the other Tamagotchi who receives a snake or something like that replies with the answer, behave yourself. But this is alternative. So this meaning that this giving a snake as a present can occur, or it may not occur. So this is why we need this alternative box here. And now here we see a similar picture. We see a critical region, and this is about playing between Tamagotchis. So here the first Tamagotchi asks the second one, may I play with you? And now after that we enter the alternative. And the alternative is between two options. So the first option, where the second Tamagotchi asks to play with the first one, and that interaction then captures playing between the two Tamagotchis. And the second alternative here is when the second Tamagotchi asks the first one, sorry, I'm not in the mood for playing right now. So does it look complicated? Or does it make sense?
Probably not complicated, but too detailed.
Too detailed, yes. So, and why, now I can explain why it is too detailed. Well, it is because here we represent not just interactions between these agents, but we also represent some elements of their behaviors. And these elements of behaviors, they refer to the mental states, or they refer to the knowledge basis of those agents. And the elements are here. Enough presence. So this is something that the first Tamagotchi who is about to give a present knows. Only the one, I mean, who is about to give a present knows how many presents it actually has got for giving away. So maybe there are some presents it wants to keep just for himself. So, but that's up to him. This is actually a part of its private knowledge. So what presents have I got, and or let's put it this way: what items have I got, and what items out of those the items I've got I'm willing to give away as presents. So this is the private part of private knowledge by the first Tamagotchi, and meaning that only the first Tamagotchi knows about this, and this is why this is actually. that enough presence is an element of behavior rather than element of interactions, because it refers to the knowledge state of a particular agent, and it refers to the decision making by a particular agent. So this is the reason. And the same thing is true for, not really here. Well, there is another condition, connection operational, but that connection operational, that doesn't refer to a knowledge state or behavior of a particular agent, but that refers to the kind of technological issue, the infrared connection between the two agents. Of course, for example, when we see this plane between two Tamagotchis, and we represent alternatives here, then the reason why one or another option may occur, the reason why the other Tamagotchi might be willing to play with a friend or might not be willing to play, the reasons also have to do with mental states of that particular agent. So in the given case, it is up to that Tamagotchi, up to that mental state of the second Tamagotchi, if it is willing to play or not. So, and in this sense, we are here also referring to behaviors and decision makings by particular agents. But we do not represent here as an explicit condition, but we are actually referring to the behavior of the second Tamagotchi. And also the same thing here. Then when one Tamagotchi asks the other one to accept the present, then whether the first Tamagotchi gives a proper present or whether it gives something like a snake, inappropriate present, again, this is up to the behavior by the first Tamagotchi. But we do not represent here by means of an explicit condition. And also here, so whether the second Tamagotchi accepts the visit or not, so it is up to the behavior of the second Tamagotchi. Well, of course, it goes to a predefined rules, which is that if the age of the first Tamagotchi is smaller than the age of the second one, then the visit is refused. But it is still up to the behavior of the second Tamagotchi to accept the visit or, in contrary, refuse the visit. So this is the reason why we are calling these models protocols, because they are, on one hand, they represent interactions between agents, but on the other hand, they represent some behavioral elements of agents that refer to the knowledge states of those agents. So it's kind of combination of interaction and behavior models. So are there any questions about this? Again, I'm not going to ask you to create models of this kind, but this is just to show you what kinds of interaction models are available. Okay, then a few more models, and then we are getting to our practical exercise. So this is the simple interaction model, or pure interaction models for grocery shopping, and this is between a shopbot agent, the agent helping a customer on one hand, and the coordinator agent on the other hand. And here the shopbot asks the coordinator to give a price for product X in store Y, and the coordinator gives that price for product X in store Y, and here the shopbot asks the coordinator to give quality evaluation of a product X in store I. It can be also quality of service evaluation of that for the particular store, and the coordinator agent returns this aggregate quality evaluation of product X in store Y. And of course, these interactions are repeated for different products and different stores. So both of them are actually executed many times, because the shop bot needs to get an overall picture of prices, as well as qualities of products and quality of service at different stores, in order to efficiently help its owner, its principal, in decision making. Because the problem is that the owner needs to make a decision which grocery stores to visit, and the owner uses the help of his or her shopbot agent for that, and the shopbot agent turns to the coordinator agent, who has an overall picture about prices, as well as qualities of products and quality of service of different stores. Yes?
Do we always need to specify actually both parties? Because look at the diagram. For coordinator agent, is it important who sends the message about giving the price? Because tomorrow it may be another type of agent appear, like statistics agent, and it will also ask the same question, please give price for product X. And if we divide the diagram, we make our system like more universal, so-called. If it's important that we answer only to shopbot, then we probably can include it in the outgoing message that reply price for product X only for shopbot, but for the everything else we decline. So thus we are losing couple. We presume this loose coupling strategy or approach that usually used in software development. But can you?
You mean? So this is a question about coordinator interactions. Yeah.
Yes. If we split the picture on twice and just look at the certain entity like coordinator agent, what kind of messages he can consume, what kind of messages he can produce, and doesn't matter what's the rest. It's like a bus of the messages. We don't know who will issue the message probably.
Yeah, but this is now, you are now talking about behavior models. That is different. Yeah, that is behavior models. But I mean, in order to gain an overall picture, we need both interaction models and behavior models. So we're going to do that as well on Friday. We're going to model this behaviors by individual agents that also actually entails messages received by those agents. And the behavior model basically represents what will happen if an agent receives a message of a particular kind. So what will happen? What will the agent do after it has received that kind of message? And also with behavior models, we can represent proactive behavior, meaning that what kind of actions will the agent initiate based on the state of its knowledge base.
So behavior model actually encapsulates the interaction model?
Not exactly. Well, they are just different views, different perspectives to the same system. Because here with interaction models, we concentrate on what happens between agents, what messages they exchange. But with behavior models, we concentrate on what is going on inside agents. What is the kind of intimate life of an agent? I mean, how it makes decisions. So they're just like two sides of the same coin. But here, of course, you can do it more efficiently. Maybe we could actually combine this message for messages of asking prices and quality evaluations. And of course, there are other architectural solutions possible. Though in the given case, the architectural solution actually prescribes two types of agents, shopbot and coordinator agent. So it is a partially centralized system rather than being a pure peer-to-peer system here. But we could actually implement it or design and implement it as a peer-to-peer system, having just shopbot agents and not having the coordinator agent at all. What is more feasible? So I don't know. I mean, this It seems to me that maybe having this kind of coordinator agent is more feasible because there are so many stores and so many products and so many experiences by customers that need to be registered, so that it would be overwhelming for each shopbot to do that. So that's why I think it may be feasible to have a coordinator agent, but the solution with just shopbot agents assisting customers is completely possible. So, and maybe there is some third option available. I mean, how this kind of system could be implemented. By the way, what those of you from Estonia know, but other students may not know that in Estonia there is a kind of movement by retired people who actually, well, retired people have a lot of time as a rule. So then, I mean, they go to different stores, the people taking part in that movement, and register prices for groceries. And then they put this, the prices up on a website. And now everyone can actually consult that website and see what the prices are. Well, it works, but it is manual, and it's pretty actually pretty industrious, I mean, to do it, because someone has to go to the store and register the price, and there is no automation of any kind involved except the website. So and I remember that once these elderly people, I mean, who lead the movement, we interviewed on the Estonian morning TV program, and then actually the interviewer asked if I mean everyone, especially young people, if anyone could come up with a more automated solution. And I don't know, so far no one has reacted, because the crucial problem here is how to register prices on stores. You know, each product has a barcode, but these barcodes do not include prices as a rule. So this is the problem here. Of course, it will be solved one day by RFID tags, I think. With RFID tags, it will become easier, and I'm quite sure these tags will include prices as well. And on the other hand, there are plans for introducing electronic recipes in Estonia, so that all recipes would be stored in one central database, and everyone who is interested in a particular recipe can retrieve it from there. And again, here by using some actually technologies of data mining, for example, similar results can be achieved. But the problem is the entity who actually is responsible for the database and who manages the database, is that entity willing to actually give away the information for even in the aggregate form? Is it willing to do so? So here I'm talking about social information systems where that actually is founded by customers and belongs to customers. So there is no this kind of problem because stores are not included. But if stores and some other entity managing the database is included, so all this picture will become more complicated. Okay, and now we're just on time for teamwork. The teamwork comes in two parts. Okay, let's do it. Okay, I'll show the first part. So the first part was, please decide the types of agents for the product idea of your team and model acquaintances between the agents. So you do not need to create these agent models as tables, but just decide the types and show the mapping between roles and agent types graphically, for example, in the way it was done here, in this way, for example, and show acquaintances between agents. I mean, who interacts with whom is the question here. And for this, you can use an A1 paper or a word processor of your choice. Well, it is just about a simple drawing and time allowing continue working on your goal model, role models, organization model, and a domain model. And I think you should put a particular emphasis on the goal model, because that is something you will need on Friday. But also other models in order to obtain a complete picture. And then the second part of the exercise, I'm sorry that this is now in 2 parts because I didn't know in advance how it was all going to work out here. But the second part is create pure interaction models for the product idea of your team. By pure interaction models, I mean just model interactions in a very simple way, like it is done here. This kind of interaction model. Just showing, I mean, how these different software entities or agents interact with each other and how they interact with humans in your product. And again, use A1 paper or Microsoft Visio stencils for AOM and time allowing, continue working on other models. So, thank you. And so I will be around and please ask for advice. Thank you.